Okay, for this video, we're going to get back to our current unit on Taylor series. A little bit of background first. For the geometric series, the sum of 2 times 1/3 to the nth. Notice it is an infinite geometric series that has a sum. This converges because that r is less than 1/3. I want to find S4, which is a shortcut way of writing the sum of the first 4 terms, and S infinity. Now, there is a formula for finding S4, but I'm going to leave that alone for a minute because it's pretty easy to just list the first 4 terms. We've got 2 plus 2 times a third plus 2 times 1/3 squared plus 2 times 1/3 cubed. And that would be 54 over 27 plus 18 over 27 plus 6 over 27 plus 2 over 27. (54 and 18 is 72, 78, 80 over 27. Which, oh, that's big. Just to get a nice decimal approximation here, 80 over 27 is 2.9629. Okay, nice and simple. If we're going to compare that to S infinity, or the infinite sum, well, luckily we have a formula for that. The infinite sum is A1 over 1 minus R, which is 2 divided by 2/3, which is 3. Okay, so our actual infinite sum is 3, and if we only add the first 4 terms, we're up to 2.9629. Hey, you know what? That's pretty close. Not bad for only adding 4 terms out of a list of infinite numbers. What we're going to introduce ourselves to today is this idea of an error, which just means the difference between the actual infinite sum and the approximation we get after adding only a certain finite number of terms. Sometimes it's called the remainder. That capital R is for remainder. So R4 means the remainder after 4 terms. So all we need to do is subtract 3 minus 80 over 27, which happens to be 1/27. Okay, not bad. Visually speaking, what we have here is, if I were to, actually we'll come back to that later. Okay, that's a simple idea. We can find the exact error. Here's the problem. We can't usually find this because we can't usually find the actual infinite sum. We can find the infinite sum of a geometric series, no problem. But for most infinite series, even the ones that do converge, we have trouble calculating the actual exact sum. So what we're going to do instead is estimate the error. And then you'll see why we might want to do that in a second. So there's this term called the error bound. And it sounds more complicated than it really is. An error bound is the maximum amount a partial sum could differ from an infinite sum. It's the biggest amount an error possibly could be. Where we're going to see this pop up is in the context of Taylor series, when we're using an infinite series to rewrite some other function, like when we take e to the x and rewrite it as a power series. The idea is, if we want to find out what e to the third is, we could take the number 3 and plug it into the power series. 1 plus 3 plus 3 squared over 2 plus 3 to the third over 3 factorial plus 3 to the fourth over 4 factorial. We could do that. And however many terms we stop at, we'll be off by a certain amount. That we're not sure exactly how much that amount would be, but what we will say is we will call the maximum amount that error could be is called the error bound. It'll make a little bit more sense when we see some examples. If you want to see this in a slightly different way, it's a little bit more visual. You can think of it this way. An infinite sum is broken into two parts. We've got our partial sum, and then which is everything you've added so far, and then the remainder, which is everything you haven't added yet. So, for example, if I have a partial sum of 3 terms, it will be the sum of the first 3 terms, and then the remainder is everything else. The error bound is all about figuring out how big all of this might be. Because we don't usually know exactly what R3 is, we can't calculate that. We don't know exactly what the infinite sum is either. Like the two are dependent on each other. But if we know the error bound, if we know the biggest possible amount that that remainder could be, we say the biggest amount that the remainder could be is E, we'll call that the error bound, which means the infinite sum must be somewhere between the partial sum minus E, if our error is in one direction, or the partial sum plus E. In other words, a diagram might help. If we take the partial sum after 3 terms, what we're doing is using 3 terms to approximate the infinite sum. But we could be off by a certain amount. That amount is E. Which means the actual infinite sum is somewhere between S3 minus E and S3 plus E. Somewhere in that range is the actual infinite sum. We are going to see 2 different ways of calculating that error bound in the next 2 videos.